fire up the machine, go live. Cool. Let me just share that in Twitter real quick, and we get set up with Algebra stuff. I just have 45 minutes, literally 45 minutes today, but we'll make the most out of it. Where do you want to go? Stream Manager. There you go. These. I don't know why it's under the edit button, but we'll tweet that. Boom. Awesome. What do we do today? So first of all, I fixed right after the stream. First of all, why isn't the environment activated? Terminal, new terminal. I thought that was happening automatically. There you go, automatically. Cool. So Jupyter Notebook. I gotta learn how to type without looking at the keyboard. That's looks like a good skill to have, which I don't. But what we're going to be doing today is further experimenting with the splitting and the expanding here, because I've already now I realized one of the consequences of getting rid of linear algebra is the fact that now we actually have to deal with a single qubit case specifically, which I hadn't before. This means, splitting actual single qubit nodes into edges. It's something that the entire library does not currently support. So this is going to be work for later for sure. Notebooks. This is where we are with the testing. There you go. So what I did last time is it worked. Oops, I hope that terminal didn't fuck up with these now. They're still working, right? Even if I close the terminal. Run all. Yeah, awesome, perfect. So it works, right? So what this is telling you is there's one qubit, right? Qubit 0, and so when you run the Hadamard rule, it just puts the qubit state into superposition because that's what the rule tells you to do, right? It matches a zero ket, and it puts a plus ket. But when we apply the X rule, then it does what I expected it to do, which is it basically splits the node into two nodes, and one in the 0 state, one in the 1 state, and it applies. Yeah, well, it applies the rule, right? Because that's what it's done. It's basically, there's no difference in terms of where the rule is applied, right? Like the 0 turns into 1, the 1 turns into 0. So that's why you have still a 0 and a 1. I wonder if I would see anything. Probably I would not, because it probably would be sensitive to print. It would be sensitive to actually print the amplitudes just to keep track of. The problem is the way I did it here is not so comfortable to do that. So per edge, we do all the qubit labels, and at the end we print. Okay, and at the end I print basically amplitude. So amplitude self edges E. Is it amplitude? I think it's amplitude. So I print, and here I don't because it's the system edge. Yeah, but actually, I never thought about what the implications are of having a system edge that doesn't have an amplitude associated to it. That's something to keep in mind as well at some point. Um, awesome, perfect. What are we doing? So yeah, let me reload this stuff. Kernel, run all. So what I want to do is I run the X rule first, run the Hadamard rule afterwards. Yeah, so that kind of makes sense, right? Because the edge that has the minus is the edge that's in the zero state, which is, here if I do a print roll here, which now I can do easily because there's no something like these, right? So the minus is in the one component, and here the minus is in the zero component. If I were to factor these things out now and actually get the thing that I want, which is back there would still be the plus, it would still be the plus state, but it would have the minus on the zero component. But I can't merge them because my factoring method does not account for edges with one qubit. That's the problem. That's the next thing that I need to work on. But first, we're trying to see whether this works at all, right? So cool, that's good. Um, what else should I test? So what am I testing at all? I mean, I'm testing that the rules work and that it's actually doing the expansion as it should, right? So I'm trying it with one qubit case and it seems like it does. Now the contraction or sort of the factoring, it's the next step. I first want to make sure the expansion works across all the use cases. So it seems to work for one qubit, right? This means we get, so I get a qubit in the plus state, and then what the X rule does is it splits it because it's not in the Z basis, and then it runs a rules through the system, which turn the one where the minus was into zero and blah blah blah. So that all works well. If my system is in the Z basis, like things stay like it's just one edge. That's the system edge, right? Yeah, that's all cool. There's no edges. I forgot the coffee. It's fine. Um, yeah. So now two edges, two nodes. Okay, now two qubits. So we've got two qubits. Let's try with two qubits. Let's see what we can get out of this. We've got two qubits. Boom, Q0, Q1, both in the zero state, right? If I apply the X rule to Q0, that one changes. If I apply the X rule to Q0 again and then to Q1, like, chill, right? So that one changes. What if I apply the swap rule, which I've never tested, which takes 0, 1 and turns it into 1, 0, 1, 0 into 0, 1, and the other cases leaves them alone. And that shouldn't split anything because it's everything in the Z basis, right? Like remember what the qubit expansion should do is it just should expand the qubit, but the actual expansion. Oh, you can actually jump to the function. I didn't know. The it's the good it's the good good features of an IDE. Actually, let me just get some light into here. Awesome. So what this does is, you know, it splits only split edge, split edge, split edge. Wait a second, actually it does do the splitting, just there we go, split edge. Yeah, so if it's in the Z basis, then There's no splitting. We like that. We like that. Rewrite. I hope it's clear what I'm doing. If not, it'll become clear soon, as I'll do a bit of a wrap up on these. But basically, if I put one qubit into the one state, let's say like this, and now I do the swap rule, and I map it like this, didn't work. That's good. Stuff to fix. Split A, blah, 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 blah. The object type bool has no length. What? Oh. The parentheses are wrong. Yeah. Cool. Kernel. But I know because it's printing split A, split B, I know that it's trying to split things. So, but actually I can get rid of these, to be honest. They're not really needed. But let's see. It worked. It worked. The swap rule worked. Neat, right? Because before the swap, yeah, it worked. That's awesome. It worked. Now, so it works if I don't have to split stuff. That's cool. What if I put one qubit in the plus state and another qubit in the minus state? That can be interesting. Or one qubit in the one state. Let's put it this way. Let's do one qubit in the Hadamard state, right? So one qubit in this, one qubit in the. So we have one qubit in the plus state and one in the zero state. And again, the printing here is still not working well in terms of I want everything to be aligned properly, but that's Q0, that's Q1. And now I would expect the swap rule to do what? To split these qubit into two edges. So you're going to have two edges in the system, one with 0, 0, and another one with 1, 0. And then run the swap rule, which just flips things around. Let's see. Okay, let's see. It didn't break. That's good. And what do we have? We have two edges. We have two edges, which is good. And the system edge is empty. So qubit 0, right, is in the 0 state here. Yeah, and it's actually it worked, right? Because if I will merge this now, the plus state is in qubit 1. You see, because it's 1 and 0, and here is 0, 0. So if my factoring would work, which in this case should, to be honest. Can I try? Can I try? Factor. How did this work? Because it doesn't work for one qubit, but it should work for factor qubits. So I just give it the qubits. Okay. So if I just say, if I now just say, you know, kind of printing the in-between steps, system factor qubits. And I give it the qubits, which is basically these guys, right? And then I print the system. I've got factor qubits, there you go. Yeah, it worked. It worked. It worked. You see? You see? Boom. It worked. Awesome. So now the plus state is in Q1, the zero state is in Q0. I mean, even if I, just to make sure things get state preserved and whatnot, like if I run an X rule here, so I get a minus state, yeah, then I get a minus state here as well. Awesome. Let's try to make that just real quick a bit nicer, which is in the print row, whenever I print a state, whatever I print the state in here, right? So what I should do is state equals this, right? Or not, like I should just say system simplified state, right? So simplified state, I should do this simplified state, which is a function that will basically simplified state. So what it will just do is, if self state equal if state is equal to 0 CAD, return basically a so what we're going to return, we're going to return just the, can I do that? Is that going to work? I'm a dirty programmer, so I don't care about else ifs. So, plus and a minus state. So at least I get a, for the simple cases, I get a nicer representation. If it's not, then just return a string state. Right, because that's, yeah. So that should at least make it a bit nicer. Oh, stupid. Self kernel run all, and here I definitely don't wanna, don't say if this changes this. Is this being, yeah, there we go. What? Self, there we go. Just basics, just the basics is what I'm missing sometimes, programming basics. Okay, but it kind of works. So let's try with 3 qubits. So if it's not, if it's not in the, cool, yeah. But now I don't need, so I need to figure out a better way to add the amplitudes in here. Definitely. So this is something that, kind of doesn't need to be that big. I need to definitely find a better way to do that, but cool, the amplitude, what I need to do is the other way, is the other things. I just need to get these and these, and basically, kind of if length of p helper is different than 0, is bigger than 0, then p helper append what the, yeah, so I append the amplitude in here. That's probably a better way to do this, and that's the only place where it makes sense to do this. Awesome, that's just cosmetic stuff, but okay, let's do more tests. Let's see if that runs nicely, and let's do more tests, right? Let's test with 3 qubits, but I don't have a 3 but I can build a 3-qubit gate easy, because it's just rules, man, it's just rules. It's still, why does it still write it so crappy? Print row. Oh, I haven't saved. That's awesome, right? So the rule for the rule for the TOEFL is actually pretty simple. Look at this. Minus 0 and with 0 and a minus. And here we have the amplitudes of these edges. And then this edge is just, there's no system edge. So what I should do here is, to be honest, the same, right? But just cosmetic, but it's just amplitude, you know, no real amplitude, we just say system, like free qubits. So non-entangled. But what I should do here, to be honest, is, you know, it's not just a length. What I need to do at all is system empty equals true. And so, you know, if I get one of these, then system empty is false, and then just have an overarching if here, you know, if system, if not system empty, then we do the rest. Yeah, that's better. So I don't print unnecessarily that stuff, you know. Cool. It's running. You know, that's how easy it is. Did I save? Yeah. Is this running or what? Yeah, there we go. Why it takes so long? Cool. It's cleaner. Yeah, it's cleaner. So they are non-entangled, non-entangled. I'd say not entangled. It's probably better. But anyway, so what about we write? You know, it's a bit of a. I think it's a good trade-off that you can build rules like that, so you don't have to, you know, kind of build matrices. It's much more efficient to just say, you know, you build these rules like that, so we know that 111 goes into, you know, 110, and 110 goes into the 111, right? So here we have the CCX rule, and if we have a system with 3 qubits, I'm going to keep that one there. So insert cell below, and I'm going to do a system with 3 qubits, and I'm gonna print the system. So that's all good. And now what we'll do is they're not entangled, and so what I wanted to do is I wanted to put the first two systems, the first two qubits, qubit 0, qubit 1, in the plus state. So we add a printing step in here, and I like that. And now now run the CCX. To be honest, if that works, I don't know. CCX rule, which we will map it like this. Ugh. See what happens. Okay, look at this. Well, that actually looks like it works, right? It's cool, man, because yeah, it seems like it works. And if I factor the qubits and print the system, so it's sort of optimized or the most compressed in terms of yeah. That's essentially, let's see what quirk size. Quirk, 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 quirk. So we have a plus and a plus state, and then we do a Toffoli gate. And, yeah, okay, it's fully entangled, right? But it's like, does this make sense? So what I'm saying is one edge. Like if Q0 and Q2 are 0, then the one in the middle is plus. Is this, if I do 0 and 0 and I take a look at the block sphere here, we have a plus. That makes sense. That's correct. If it's 1, 1, it's 1. That's true. If it's 1, 0, is 0. So if it's 1, 0, then the block sphere here is a 0, obviously. Yeah, and I guess that's not, of course, that's not a unique way to represent that. I'll chill, but it works. So yeah, it seems that it works. I only have to work out how the factoring of one qubit can, like whether that works at all or not. Because this is the 2 qubit example, this is the 3 qubit example, right? So this is 2 qubit tests. This is 3 qubit tests. And if I insert a cell above, we can do again sort of the 1 qubit test, right? Where I put a qubit, so we have just one qubit, right? We print the system. Then we have a, I'll do these things here. So I'll actually copy the whole step in here, right? So that gives us a minus state. And now we want to do a next gate, right? So the X gate will be just like that. And that leaves the system with the amplitude in here, right? Because we keep always the amplitude simple there. And now the idea would be factor qubits and see what happens, which I guess it might not. It worked? What? It actually worked? It is a minus. Yeah. What? That actually worked? Like, it would be cool to print the global phase, to be honest. It would be cool to print the, that it actually has a global phase to it, but it's not super urgent. But what? That worked? I definitely got to revisit these methods because I'm not sure that, how can I make this? This is just, the space in here is just these, right? So I should just like, just like that. And if I reset, so it just looks nicer because I'm going to be mostly working with rather simple numbers instead of just complicated things. I know that the as soon as I get something more complicated in here, yeah, it looks better. So what about I just what about I just, kind of, do something like this. Stupid cosmetic stuff, but, and probably I want to do the same at the end, actually. To kind of close the, oh, it got the right. Okay, cool. So if I don't have to have these separations printed in here, right? Yeah, okay, but hmm. What they say, hacks are the best. That's so dirty. That's so dirty. That's not how you print stuff. Anyway, good. So actually, I can get rid of these things probably as well, and these things here. Opa, not these. What? Okay. Yeah, that's nice. A bit too much for the 1 qubit case, but that's okay. Okay, so yeah, looks like basically the tests it's working better than I expected. I just feel like this maybe something a little off in terms of, well, I can always print the state vector, right? State vector to state vectors. I can always say print raw, print raw here. Just below, what do we do it? Just yeah. So just here, we kind of like print self to state vector, and see if that looks nice. But yeah, so this is a not a bad way to test stuff. Awesome. How is the NA looking like? If I add a okay, so now I have the state vector and I can check as well, the things are correct. What if I add like a 4th qubit in here? How would that pop up? Okay, so it stays here. Like factoring does not take it out, and factoring should take it out. That's a thing. You know what I mean? Like it should just be because this qubit is not entangled. So that's definitely, yeah, that's maybe the next thing to do is to dive into the factoring. It's not entangled, not entangled. 0 minus state, exactly. And so, but here, like, Q0, 1, and 2 are entangled, but Q3 is not entangled. So I definitely want to take that 0 out into another row that's like NA and not applicable, not applicable, not applicable, and then 0, right? Cool. Yeah, but I mean, that looks pretty nice. I mean, I don't know, is that it really? To just take out the linear algebra? Is that all that it takes? Just, what have I done? Let me just maybe, commit that. New terminal. So, okay, commit. Basically, testing rules and no linear algebra. Okay, push. That's cool. What have I done though? Basically, I've built the, so we've got the simplified state concept, we've got the print row, we've got the is match, replace match, rewrite concept, right? So that seems like it's working, right? So what the rewrite is doing is, what it's doing is first of all, it sets all the tracking. Oh, maybe let's try to visualize the tracking. Yeah. So what about in the print row here? So what about um, the stuff that something changes? Maybe I'll mark it with a star, something like this. So if the node is replaced, right? I guess here I can do that. It's like if, yeah, okay, so that shouldn't be the state. That should just be, or I can do this, yeah, no, I can do this here. Say, replaced, it's just this, and then um, if this is replaced, then replaced equals like a little star, and this is always going to be replaced, right? And hopefully the replaced is true, and that's not, okay, cool, that's not turned off. That makes sense. It's turned off at the beginning. So nodes, edges, and then what else is this happening? Print row, so through all the edges, and then we go through these here as well. So system empty, but also, you know, if you replaced, then basically replaced. So what this should do is, you know, for every time that we run and print something, we should see what has changed, hopefully. Oh, some indenting. Line 683. 683. Some indenting. Where is the indenting problem? Yeah, well, that's not supposed to be indented. Oh, wait a second. It is supposed to be indented. Why not? Replace this like this, and you know, if replace, then replace like that, and here it is supposed to be indented. That's correct. Why it's not? Kernel run all. Oh, that worked. Okay. Yeah, okay. So this is what changed. Then the two things changed. That makes sense. And here, yeah, we're seeing what changes, right? So this changes. So Q1 is the only one that changes. And here we see that the operation changed these three elements only, right? I'm not so sure about like whether you should flag the, no, that's probably not. That's just the stuff that it's being changed by the operation. I don't know how useful that is, but yeah. I guess I could just also leave it like you know, um, just with a space, just with a space here, and then kind of just add like, a bit of space all over the place anyway, kind of here and here, whatever. Yeah, but that's just been, yeah, that's just cosmetic stuff. That's all, I guess, all cool. Well, we now needed what I'm doing next, I'm going to drop it here because I think I didn't expect that I managed to get that tested up to 3 qubits, but it seems to work, at least for these rules. Um, there's two things next. I want to just make sure that I can round everything up a little bit more. And, basically all the stuff that is around factoring and the namings and whatnot, and then kind of make sure the measurement works as well, do general testing, and also merge. There's a couple of things here with the creation of the edges that I'm not super sure they work the way I want this to work. For example, as I said, right, we want to make sure that that the zero is kind of out and it's moved out from here correctly. And I think that doesn't happen because of this part of the code that's commented here. That's kind of doing the last mile factoring, so to say. Yeah, basically all these. And so when this is done, there's two major milestones ahead. One is merge the stuff from Jordan. Jordan is helping me with the project a bit on the things like visualization and stuff. So I've seen a pull request where he you know is separating the visualization stuff and is making some of the things better in general. So I should merge that as well. And then the next thing to work on is for sure, um, once all this is well done and worked, then we can start tackling you know bigger dimensional systems, like not just qubits but kind of have registers actually, and have 2, 3, 4, 5 numbers in here instead of just one, right? Because this will allow us to implement rules like modular exponentiation and things like these with this kind of system, which is a more intuitive way of um, defining the operations. Because I can mathematically then do something like, ideally what I like to do is like, for example, the modular exponentiation rule. It would just be a rule that says, you know, um, for example, like match X, right? That's a symbol. So this means kind of match every edge and assign that value to X, and then or something like these, right? And then it's like you're saying match X and I don't care about Y, and then um, sort of keep X and do or match X and Y, yeah, and then do leave X and then do replace the Y by something like these, right? So ideally, like and I know this is obviously not working now, but I know there's a lot of nuance in here, and I know that you might end up building something that is not unitary and whatnot, but you need to work out these in general. But like this would allow you to then build prototype Shor's algorithm really quickly. And remember, the goal of these is to have a tool that can be used programmatically to explore algorithms and to kind of build things and see how the evolution is, how the different registers look like, how the entanglement looks like, and analyze kind of what's happening in there, right? So that's kind of my ideal goal, is that you can do stuff like these. And then, that is the quirks equivalent of doing, these and then taking these, right? And defining R, and we're not like as default value B mod R. Needs to input B. Yeah. And B, exactly. Like this is ideally what you want to do. Because the problem with the graphical interface like Quirk is that you you're limited with the qubits, right? You're limited with these. You can do it, of course, you can work at the register level and whatnot. It doesn't really matter because you can use displays, and displays already do the job for you, right? Decimal 0, decimal 1, decimal 2, 3, 4, blah, 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 etc. But I want to have more insights into the entanglement, and that's something that I don't know how to get into in the interface. I really don't know. Yeah, I don't know. Maybe it's a bit of a bit overblown to do it like these, but at least you can have a bit of a visual way of how the entanglement is evolving, how things look like. We'll see. We'll see if that becomes useful to explain algorithms or to explore algorithms. I believe there's a nice way to explore a Grover's algorithm like these as well. So anyway, I'll leave it here. Thanks for joining. It was 45 minutes to the point. We actually made it, so I'm happy. See you next time.